Hello there and welcome to the series of videos going through the content of A-Level Maths. Here we're looking at the binomial distribution so we can answer questions from exercise 6b. Now there are lots of different types of probability distributions, probably an infinitely many number of probability distributions. We're going to start with the most simple case, and the binomial distribution, reading the word bi, so bicycle, two wheels, binomial distribution means that there are only two possible outcomes, and we're going to look at the probabilities given that we've just got two possible outcomes for a given situation. But then we're going to scale it up and do multiple repetitions of this probability event. So therefore we're going to calculate probabilities up to quite a high value, but this here we're starting on the most simple probability distribution here. So what we've got to bear in mind is when we're doing probability distributions, we've either got effectively a success and a fail. Okay, so a win or a loss, a pass or a fail. Okay, so those we've only got two possible outcomes. And here's a classic situation in which we have a binomial distribution. Gary is playing a chess with Nigel and has a 2/3 chance of winning the game. If they play 5 games, what is the probability of Gary winning? Exactly 3. So what we could do is write out all the different combinations, but that would take a long time, especially if we have really high numbers. So we have 10 different ways in total here. So the probability of the first combination listed can be calculated like this. So effectively, if you think about a tree diagram, you could have 3 branches where Gary wins all 3 of these matches. But if they're playing 5, then Nigel's got to win 2 of them. So Gary loses 2 matches of chess. Okay, so this is how we would work them out on a probability tree diagram. But on a tree diagram, if you remember, there are going to be lots of different routes that we can take down that tree diagram. We could start with a win and then a loss, and maybe 2 wins and then another loss. So what we need to think is there are going to be 10 ways in which this probability can be calculated, because we've shown that here. Each one of these way of Gary winning 3 events could effectively be representing as a route down a probability tree diagram branch, where we've got probability of Gary winning as 2/3, probability of Nigel winning as 1/3. So effectively what we've got here is 10 branches down a tree diagram route, and we've got on that tree diagram route Gary winning 3 times, so that's 2/3 to the power of 3, and then 1/3 for Nigel winning to the power of 2. Why are we doing powers here? Well, remember that we times along the branches of that tree diagram as we go along, so therefore we've got to times 2/3 by itself 3 times and 1/3 by itself twice. So that's why we're doing powers here. So effectively what we have here at the front here is the 10 represents the number of different orders that this win and loss can happen, times the probability of winning to the power of the number of wins, and then we've got to counteract that with counting our failures. So that's the probability of failure, or probability of losing, to the power of the number of times we've lost. Okay, so it's a simple way of calculating the probability here when we take lots of different combinations into account. Okay, so this topic links quite heavily with the binomial distribution that you've seen in pure maths, where we expand brackets using this factorial notation here. So where we see that we're expanding the bracket with a power of 5 on it, 5 choose 3 is how we would work out the coefficient on the x here. So therefore we can just use the 5 choose 3 button on our calculator to work out that 10. So do we see here how they're heavily linked to each other? Effectively what we could say here is x can represent success and y can represent a loss. So effectively you've got 3 successes, 2 losses, and the number of different combinations that this can happen in is 10, and we can work that out using 5 choose 3. Okay, so it's very similar here to the binomial expansion. Okay, so let's have a look at the ground rules for a binomial distribution here now. So the binomial distribution has a number of conditions that must be met. There must be a fixed number of trials. We must have to say that we're going to perform this experiment 12 times, or we're going to perform it 5 times. An example where we can't use a binomial distribution is, for example, the driving test. If you take your driving test until you pass your driving test, then we have no set amount of number of times that you're going to take your driving test, because if you pass the first time, you're not going to take a second driving test, are you? That'd be pointless. So we must need a fixed amount of number of trials, or the number of times we're going to perform this experiment. There must only be 2 possible outcomes. You can think of this as success and failure. And the probability of success is the same each time. So if you're successful once, in real life you're probably going to be successful more and more and more. Or if you fail the first time, you're probably going to learn from your mistakes and then become more successful later on. In this case here, the probability of success is going to be the same continuously, on and on and on and on. It's effectively like rolling a dice. Just because you've got a 6 in your first go doesn't make you a really good dice roller to get a 6. It's a random event. You're randomly rolling the dice to get a number on it. Okay. And the trials must be independent of each other. So one trial, a success or failure, does not affect the other one. Okay, so the way we notate the binomial distribution here is with a capital X. Now we've seen capital X's before in the probability distribution that we did before this video here. And then what we need is a little squiggly line, and then B to represent binomial. Now we're going to see lots of different probability distributions in this A-level. We're going to come to the normal distribution in the second year, so that's why we need to define it with a B, because there are lots of different probability distributions, so we need to write down that we are using the binomial distribution here. N here, whoops, let's just ignore that for a little while. N here is representing the number of trials, so if we're flipping a coin 5 times, N is going to equal the number 5, and P is the probability of success, where if it's a coin, for example, then that success is going to be a half, so we'd write a half here. So if we have a binomial distribution, then the probability of a certain number of successes, we'll call R the number of successes, is equal to, and this is a really important formula you'll need to remember, N choose R, so if you have 10 trials and you want 8 successes, then it'll be 10 choose 8. And then it's the probability of success to the power of the number of successes times by the probability of failure to the power of the number of failures. Okay. So N is the number of trials, P is the probability of success. The probability of getting R successful trials is the number of ways of choosing, the number of ways in which we can order those success and losses. So this here is effectively the number of ways that we can order those successes and losses. And then it's probability of success to the power of number of successes times the probability of failure to the number of failures. Okay, so there's lots of different parts to that formula. Hopefully as we see more questions we'll get familiar with number of successes, probability of success, number of failures, probability of failure, how many different ways can this be ordered, put that at the front. Okay, alright. Oh, it's in the Formula A-Level booklet section. Great, so we don't need to remember, but I would suggest you remember it because we need to use it very frequently. Alright then, so going back to our situation with Gary and Nigel, the way that we would calculate this using the binomial distribution is we would first define our binomial distribution. That's really important. It's effectively one of your method marks that you'll get for each question. X here is binomially distributed 5 trials with a probability of success of 2/3. Now the probability of each success here, and what we're going to look for here is 3 successes, is equal to the number of ways that these 3 successes can be ordered, 5 choose 3, times the probability of success to the power of number of successes, times the probability of failure to the power of the number of failures. And you can type that all into your calculator and you get out 0.329. Perfect. Okay, let's have a look at a different situation here. Effectively, we're now rolling a dice, probability of 1/6, and we're rolling it 12 times. Find the probability of getting exactly 2 6s, or 2 of the number that we desire, exactly 9 of the number that we desire, and less than or equal to 1 on the number of times we want to the outcome that we desire. Okay, so in this case here we have n number of trials, p is the probability of success. So for A, we're going to have here the probability of 2 successes equals 12 choose 2. That's effectively the number of orders that these 2 successes can happen in, times the probability of success, which is 1/6 to the power of 2, times the probability of failure to the power of number of failures. If we've got 2 successes out of 12, we've got 10 left over. So these 2 powers here and here should always add up to make the number of trials, because we've got a certain number of successes and a certain number of failures. Put that into your calculator and you get 0.296. Okay. Yeah, so remember, this is how it's notated on your calculator. It's 12, then the choose button, and then a 2. Okay, the next one here, probability of exactly 9 successes on our dice. So we do 12 choose 9 times the probability of success to the number of successes times by the number of failures to probability of failure to the number of failures. 9 add 3 equals 12. Great. Work this out on your calculator, and that's a very low probability. Effectively, because this probability is so low, we're not expecting it to happen a high amount of times. 9 successes, when you've got such a low probability, is going to be very, very unlikely. The next one here is the probability where we've got less than or equal to 1 number of successes. So for the moment, the only way that we can do that is split it up into the options that we have here. So either we have 0 number of successes or 1 number of successes. And we'll have to work out the probabilities for those individually. Now just remember, for the 0 one, effectively there's only one branch that you can go along if you want 0 successes. It would just be fail, 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 fail. So it's effectively just the probability of failure to the power of number of failures. You could put a 12 choose 0 at the front here, but remember, anything choose 0 is just 1. And then this isn't a fraction here, that should be a choose. So this is 12 choose 1 times by the probability of success to the number of successes times the probability of failure to the number of failures. And we calculate all of this on one calculation and we get 0.381. So because the probability is so low, we're not expecting many successes. So that's why we've got a relatively high chance, 38%, that we get either 0 or 1 successes. And usually a binomial distribution question is given in an example. So the probability that a randomly chosen member of a reading group is left-handed is 0.15, 15%. A random sample of 20 members in the group are taken. Suggest a suitable model for the random variable x, the number of members in the sample who have left-handed. So here we can consider there are 2 possibilities, left-handed and right-handed. The number of trials is fixed because we're only choosing 20 people, and we can assume that each member on the sample is independent. So 3 components here. Check that there are 2 possibilities. Check that there is a fixed number of trials, and that each member in the sample is independent. Those are your 3 key points there. Fixed number of trials, 2 possibilities with given outcomes, with given probabilities, and sample is independent. So therefore, x can be squiggly lined to be 20, 0.15. Okay, let's use this probability to now work out a few questions here. So the first question is exactly 7 members of the sample are left-handed. So here we've got 20 as our n value, p is our 0.15 value, and the number of successes we want is 7. So substitute that into your formula, and we want 7 successes, so we need to do 20 choose 7. This is effectively the number of different orders in which we can pick the right-handed and left-handed people, times the probability of the success, which is a left-handed person, to the power of number of left-handed people that we want, times the number of right-handed, times the probability for a right-handed person to the number of right-handed people that we want. Put that all into your calculator and we get about 1.6%. Okay, so here part 2 is less than 2 members are left-handed. So if we have less than 2 members, then we have less than or equal to 1 people who are left-handed. If it says less than or equal to 2 members are left-handed, then you'd have to include the number 2. But in this case here it just says less than 2 members, so it's just 1 or less. So substituting these values in, we want now effectively, if we want no successes, we want 20 right-handed people. Add on to 20 choose 1, number of successful left-handed people is 0.15 times probability of a right-handed person to the number of right-handed people, and we get an outcome of about 17.6%. Okay. So if you're given an inequality, you're going to have to split it up for the moment into 2 separate components, or maybe perhaps 3 separate components, and work out those individual probabilities separately. Alright then, so that is the binomial distribution. Hopefully that all made sense. It's very new to you, I know, but just remember that formula, keep it close by to you when you're having a go at these questions, and see how you get on. We'll go through the answers afterwards. Alright then, so what I'm going to show you here is how we can also use the calculator to help work out these answers here. So, in this question here for part A, what we're going to see is that we want the probability of x equals 2 out of 8. So we're going to have 8 choose 2 to start with, and then we're going to have a third to the power of 2. Because this is going to give us the probability of success to the number of successes that we want, times the probability of failure to the number of failures we want. Now we've got 2 successes out of 8, so we need 6 failures. Now you can either do this on your calculator in the normal mode, or what you can use is this statistical distribution button here. If you press menu and then option number 7, then you're going to get to a probability distribution here. Now we don't want the normal distribution, we'll see that in the second year of A-level maths. What we want is the binomial probability distribution, so that's number 4. Click on number 4, click variable, we'll have a look at what list means later on, and then type in your results here, what you're looking for. So you want 2 successes out of 8 trials where the probability is 1/3. Now, the way I put 1/3 into my calculator here is just do a 1 divided by 3. And then you press equals and you get your answer. Okay, so it's just as simple as putting the numbers into the correct format on your calculator and it gives you that outcome. The next one here is probably going to be the probability of x equals 5. So this is going to be 8 choose 5. Times the number of probability of success to the number of successes, times the probability of failure to the number of failures. So what we'll do here is exactly the same thing. 5 successes out of 8, probability of 0.333, and we get our answer here, which is 0.0683. Okay, probability of less than or equal to 1. Now, there's a few different ways you can do this. I'm going to show you another way to what we've done so far in the video. Now, the binomial cumulative distribution is quite useful here. So you remember, so CD is referring to cumulative distribution here. We'll see this a lot in the second video on the binomial distribution. And cumulative distribution means that we accumulate the probability up to a certain value, which is effectively what we're doing here. We want the probability of x equals 0, add the probability of x equals 1. So we're accumulating our probabilities up to x equals 1. So go scroll down on your menu button to binomial cumulative distribution. We'll go for a variable again, and we want to accumulate our probability up to the probability of 1 with 8 number of trials, 0.333 as our probability, and we should get 0.1951. Okay, so there we are then. So that's how we do question 1 here, and it's useful to know that we can do this on our calculator. For question 5 here, a balloon manufacturer claims that 95% of his balloons will not burst when blown up. If you have 20 of these balloons to blow up at a party, what is the probability that none of these balloons will blow up? So 90% will not burst. So what we'll say here is we'll write our probability distribution is a binomial, and what we'll say is that if it's successful, we'll have 20 trials. Okay, so what we'll say is that the success is for it, or we'll look for it, we'll count how many burst. Okay, so if we want none to burst, then what we want is a probability of x equals 0. So none of our balloons burst, which is going to equal 0.05 to the power of 0, so we don't really need that bit, 0.95 to the power of 20, and what we can do here as well is do it on our calculator. Go to that binomial probability distribution mode, click variable, we want no balloons to blow up, out of 20, probability of 0.05, so we get 0.3585. Okay. Part B, find the probability that exactly 2 balloons burst. So if that's the case here, we don't need to write out our probability distribution again because we use the same one. We'll use probability of x equals 2, so 2 balloons burst. So in this case here it's going to be 20 choose 2 for the number of orders in which 2 balloons can burst, times by the probability that balloon will burst. We want 2 of those bursting balloons, and we want 18 balloons that don't burst, and this equals 0.1887. Okay, so there we are then. So that's how we do the binomial distribution. Hopefully that video made sense for you. Feel free to go through it again, and make sure that you have lots of practice on exercise 6b. Make sure that you persevere through these difficult questions, and particularly make sure you have a go at the wordy ones. Make sure that when you do the wordy ones, make sure you write out what your binomial distribution is. That's effectively a method mark in the bank for you if you can pull that information out of the wordy question. Alright then, well thanks very much for watching this quite long video.